Hello and good day to all judges. My name is Khairul Anwar Abdul Halim from University Malaysia Perlis. On behalf of my team members, Muhammad Firdaus Muhammad Nazri, Yuana A. Wahab, Kamrusni Abdul Razak, Nuraizina Saud, Muhammad Arif Anwar Muhammad Saleh, Muhammad Nur Ilian Rashid Muhammad Jaidi, and Tiu Sin Chat, I'm going to present our invention on the flexible conductive polymer composite based on hybrid carbon black copper field linear low density polyethylene for electronic interconnect applications. Basically, conductive polymer composites are advanced materials that combine an insulating polymer matrix with conductive fillers such as carbon nanotubes, graphene, or metal particles. By incorporating these fillers, the material transitions from an insulator to a conductor once a percolation threshold is reached, enabling electrical conductivity. It has flexibility, lightweight nature, and processability, while gaining enhanced electrical and mechanical properties has become primary intention and can be substituted to replace traditional metal-based interconnect, makes them a promising alternative for next-generation electric and sustainable technologies. Why flexible conductive polymer composite? It possesses flexibility and excellent material for flexible electronics, and when subject to mechanical deformation, it's still electrically conductive. It has high sensitivity and high electrical conductivity, which is the potential to be used as stretchable sensors with cyclic stability. With the simple fabrication process, it can be the most cost-effective material to be developed. Nevertheless, the current challenges that we possess is how does the hybrid fillers affect on the electrical conductivity, and what are the effect of conductive filler on the tensile properties. In this case, the aim and goals is basically to study the effect of carbon black and copper hybrid filler at various loading on the mechanical properties, namely tensile and hardness of LLDPE, and we're going to look into the effect of carbon black and copper loading on the electrical conductivity of LLDPE, and to characterize the morphology of LLDPE in addition of carbon black and copper metals. The novelties of this invention is basically lies within the insulating nature of a polymeric material, whereby we transform it into a conductive material by incorporation of conductive fillers. These conductive fillers establish a network structure that meets the percolation threshold, enabling electrical conductivity. Therefore, this project highlights the potential of FCPCs for electronic interconnect applications. Basically, for flexible conductive polymer composite, the conductivity of the composite depends critically on the volume content of the filler itself. This material can be processed through a melt blending technique whereby the copper and the carbon black will be blended with LLDPE at the temperature of 160 degrees Celsius for 20 minutes at 15 revolutions per minute. In order to test and evaluate our CPC's performance, several tests and characterization techniques was employed, such as tensile tests, hardness tests, electrical conductivity tests, and also scanning electron microscope. In this case, if we look the tensile strength versus conductivity, we can see that incorporation of the hybrid filler loading resulted in increasing tensile strengths, and also as the amount of the filler loading increased, the conductivity also increased. Similarly, when we plot the elongation at break versus conductivity, we can find that the elongation at break also increased due to incorporation of the hybrid filler. When we plot the modulus of elasticity versus the conductivity, however, we can see that once we incorporate the hybrid filler, increasing loading of the hybrid filler within the LLDPE matrix resulted in decrease of the modulus of elasticity. Nevertheless, the hardness of these CPCs will increase with the increase of the amount of the hybrid filler loading. We can see that the copper filler displayed as a particle shape resembling flake, while carbon black exhibited aggregated spherical particles. And we found that as the carbon black and the copper content increase, the presence of void will decrease and influence the performance of the composites. These CPCs has a lot of commercial potential application, such as in communication, healthcare, transportation, and robotics. The benefits of the flexible CPCs, including flexibility and lightweight, lead-free and eco-friendly, can be customized and tuned with a cost-effective processing, and it's a material that has durability and mechanical resilience. Our invention has received intellectual property, several scientific publications, and also industrial collaborations. In summary, addition of hybrid filler comprising carbon black and copper improved the performance of the composites. The carbon black enhanced the strength and stiffness, while copper particles provide additional reinforcement and electrical conductivity. Increasing the hybrid filler content in LLDPE composite leads to increased tensile strength, hardness, elongation, and also electrical conductivity. Nevertheless, we might find at higher loading levels of fillers, the mechanical and electrical properties of the composite may start to decrease. In conclusion, the LLDPE composites has higher tensile strength, elongation at break, hardness, flexible, and efficient electrical conductivity when combined with the hybrid filler. Thank you.